So what we're going to do now is we're going to go and talk about stamped locks and the way that stamped locks can be applied in practice to solve various readers-writer problems. And we're going to take a look at an example that comes out of the documentation for stamped locks. So this is an example you can see if you read the Java 8 documentation, the JavaDoc file, and I'll provide you a little bit of elaboration. There's also more discussion about this example on various videos on the web, which I'll show you links to in a minute. So the basic idea here is we've got this point class, and the point class has some state, and we want to maintain and protect this state from updates and reads in multiple threads. And in some of the functions we're going to provide, we're going to be reading from it. Other functions we're going to provide, we're going to be writing to it. And so we have to find a way to protect it. And naturally, we're going to use the stamped lock in order to do that. So let's start out with a real simple example. This example is not unlike the release method from your programming assignment, where you have to update something. So whenever you have to actually update something, change the state, then you're going to want to use the write lock portion of the stamped lock. And this is almost identical to what you would use if you were doing something with a reentrant lock. So you come in here, we're going to acquire the write lock, which will block until we get exclusive access to the lock. We then go ahead and update the state. The X and Y fields are set to the new values that are passed in, so we're moving it. And then finally, we go ahead and release the lock. So nothing too complicated here. This is just sort of classic mutual exclusion. If that's all stamped lock did, then you might as well just use reentrant lock, or even a synchronized statement for that matter. So there's nothing really interesting here. This is a more interesting example. This is one that's going to use the so-called optimistic reading features in stamped lock. And this is going to figure out how far away we are from the origin. So, origin is 0, 0, and we're going to see how far away we are. So it's going to basically compute the hypotenuse based on the values that are passed in here. So what we do here is we come in and we go ahead and do a try optimistic read. And if you recall, try optimistic read tries to get what's called an observation stamp. And if you were to look at the implementation of this, you'd think there's no locking going on whatsoever. What's going on here? It's just getting you back a stamp. If we looked really close, we'd see that it's actually reading from a volatile field, and that has some important properties we'll talk about in just a second. So we get back this stamp, and then the next thing we do, note that this doesn't actually acquire a lock. Try optimistic read simply updates that thread with the cached values that may be in other caches. So basically, it's just making sure that the points it's about to read, X and Y, are up to date. But there's no guarantees about ordering and so on. It's just the latest version. So then we go ahead and we optimistically read the state into local variables. So cur X and cur Y are updated. And this is typically how you use the optimistic read. The optimistic read sections typically read fields and then hold them in local variables. And we'll talk about why they do that in a second. So at this point, we have cur X and cur Y to some version of X and Y. However, because try optimistic read never actually acquired a lock, but only refreshed the values in that thread of whatever X and Y had been set to, we don't really know whether or not these values are valid, because it may have happened that in this tiny, tiny window of code between try optimistic read and when we get done with the close semicolon at the end of cur Y equal Y, another thread may have come along and acquired the lock for writing. Now, to make it even more interesting, if the other thread acquires the lock for writing but doesn't actually change X and Y, we can't really distinguish that, and therefore we just always assume the worst case. So if someone has acquired the lock for writing in this little tiny window, we're going to assume that those values have changed. And so what we do here is we go ahead and we call validate. And what validate does is it goes and it checks to see whether or not the stamp that we got back from try optimistic read has been modified to be writable in that window of time from when this was done, when try optimistic read was called and validate was called. If it turns out that it was not acquired for writing, then we're going to assume that cur x and cur y do indeed have the latest values of x and y, because nothing changed them in that intervening time. And so if that's the case, if we get back a non-zero value from validate, then we're done, and we go ahead and compute this thing. If we get back a 0 value for validate, that means that it changed to writing, and therefore we have to do something more expensive in order to be able to get the right values of x and y, the correct values for x and y. So what we do in that case is we call readlock, which is going to acquire a read lock, and that read lock call could block if somebody else is currently holding that lock for writing. So this might be a blocking call. Probably won't be blocked for long, of course. And once that returns, now we have a legitimate read lock, which means nobody else can be in here writing. And then we go ahead and do the pessimistic read. So this up here was an optimistic read. Optimistic simply means we're expecting there's no contention. We're expecting nobody's changing it to writing. A pessimistic read says we expect there will be contention, therefore we had to get our own read lock to detect and prevent that from having another thread writing at the same time. So at that point, we do a pessimistic read. That should work as long as the other threads are following the lock protocol by using a stamped lock properly. And when we're done, we go ahead and release the lock, which is now a read lock at this point. Notice that if we validated the stamp correctly, nothing has to be released because we never had a lock in the first place. Because optimistic read, try optimistic read doesn't lock anything. It just refreshes the cache. OK, so any questions about this? So the point is we end up doing the computation either on the optimistic reads, which ended up having no contention because validate determined that, or we got a read lock and actually got the real values unperturbed or undisturbed. So this is an example of an optimistic read. Now, again, it's making a bunch of assumptions, and we'll talk more shortly about some of the tricky issues here about the invariance related to this. The other thing to note is that this particular example tries to do an optimistic read. If it fails, it just immediately grabs a read lock. You could sit there and loop several times trying to grab the thing if you expect low contention. Yes, Jesse?
So say you have like a lot of values to read after you get the stamp. So is it like less likely to succeed the optimistic read the more things you have to read in?
Yeah, great question. So I think the question you're asking is the likelihood of there being no contention is the likelihood of there being no contention is increased if the block of code is very short. So if there's not a whole lot of stuff that's going on here, then the likelihood of there being somebody coming along at the same time and trying to grab a write lock is reduced. If there's lots and lots of code here and there's a big loop and lots of function calls and all kinds of things, then it probably increases the likelihood that there will be some other thread that will come along and make the write, assuming, of course, that there's contention.
In the case like this where you're only taking in the x and the y, would there like ever really be contention? Because that's such a small...
Yeah, oh, absolutely, yes. I mean, again, the point class may or may not be the best example, but if you step back from the point class and you just think about something that can be read and written to, then yes, certainly if there's other threads contending for it. And thinking ahead to the Palantiri example where we're doing the same kind of stuff, there could be situations where things are being read from and someone's making a change at the same time. Adam?
You said when there aren't many writes going on, this can be more efficient than using read locks normally. Can you explain why that is?
When there aren't many, so the question is when there aren't many writes going on. Oh, yeah, so if there aren't many writes going on, then that means it's likely that by the time we get the observation stamp, read the values, and validate, nothing will have changed. Because if there aren't many writes, they probably haven't written, right? So if that's the case, the reason why this is win, why using try optimistic read is win, is because it didn't actually acquire a lock at all. So it never, unlike this call here where we say sl.readlock, which may block if somebody else is writing, when we do sl.tryOptimisticRead, then that doesn't ever block. It's always a non-blocking operation. The line of code is like one line of code that does that. It just basically, reads from a volatile field in the StampedLock class which forces a cache update for that thread, but it never blocks, other than do the cache update. Yeah, those are great questions. We'll talk a bit more about this. This turns out to be subtle, and there's some tricky issues that are not shown by such a simple example as the one we have here. Now, this third example, which is the so-called conditional write example, this is the one that's most like your programming assignment. So let's talk about it. So what we're trying to do here is we're trying to move the point to a new location. And we want to do this atomically, obviously. You don't want to have something where you move just the x and not the y, right? We want to make sure x and y are both moved together. And we're going to try to do this in an optimistic way. And this is what's called read-lock upgrading. So we're going to come into this thing, and we're going to first acquire a read lock. Now, we're going to acquire a read lock because we really want to make sure that what we're reading is, in fact, valid. We could do the optimistic read, but that would get even more complicated. So we're just going to do a read lock. So we're going to block until we get a read lock, which remember is a non-exclusive lock. There could be multiple threads that are reading at this point. And then with the read lock held, we're going to examine the state. Now, it's fine to examine this state with a read lock held because that state is not going to be changing, because nobody can be writing to it while we have the read lock held. So what we're doing here is while x and y equals 0, we're going to try to upgrade this thing to a write lock so we can change x and y. If x and y are not 0, then let's just bail out, because we're trying to move if we're at the origin, right? So if x is 10 and y is 20, and we do move it if at origin, it's going to fail, right? Because it's not at the origin. So the read lock is held. We can do a read. And depending on the state, we either just drop out and we're finished, or we give a shot at trying to see if we can upgrade to a write lock. Because remember, we're going from the situation where we're reading something to a situation where we're trying to change it. So that's the classic scenario under which the lock upgrading might make sense. So then what we do is, if the state is so far in our favor, then we go ahead and try to convert the stamp to a write lock. Now, this will not block. Try to convert to write lock will not block. It'll return a stamp, and depending on the value that comes back, we know what happened. So if we get back something that is non-zero, that means we succeeded in upgrading to a write lock. And what that means, of course, is that nobody else owned the lock for writing at that point. So that's actually pretty cool, because try to convert to write lock is a really fast operation if there's no contention. Because basically all it does is it just changes the stamp to say it's a write stamp, not a read stamp anymore. Hamid?
Why does, so try to convert to write lock, if succeeds, it returns a totally new stamp?
It returns a stamp. Well, you don't really know or care what it does, but under the hood it basically sets a bit. So the bit it sets says I'm a write lock now, whereas the bit that was set before was the read lock bit. So that's what it does. It just basically changes the state of the object to be a write versus a read lock, which is just like literally changing a bit. So it's not expensive at all. If it succeeds, right? So if it succeeds, then now it's a write lock. So we update the stamp to indicate we're a write lock, so we can do the write unlocking properly. And now with the write lock held, we can move x and y to their new values. And then we break out of the loop. So at that point, we're done, except for the cleanup code at the bottom. OK, now, if we were unsuccessful at being able to upgrade, now we have to do some more expensive stuff. So what we're going to do in that case is we're going to unlock the read lock. Remember, we'd acquired the read lock originally. Now we're going to unlock the read lock, and then we're going to go ahead and try to get a write lock. Now, a bunch of things to remember here. This is really, really, really important. There's a window of time between when unlock read occurs and when write lock occurs. So the moment, the nanosecond or picosecond that you unlock the read lock, another thread could swoop in and get in this critical section and do some stuff. So the key point there is when we call write lock, we may block because somebody else may have a write lock on it. But even more importantly, once write lock succeeds, we can't assume that the state is what we want it to be. So just because it was 0, 0 before, by the time we get down here and require the write lock, it may have turned to some other value because somebody else may have snuck in and done the change to some other value. So it may no longer be at the origin. So because of that, we have to loop back around again, now with the write lock held. So now we're in good shape. And then we go ahead and check to see if x and y are the right values. If x and y are in fact 0, either because they never got changed in the first place or because they've got changed back somehow, at that point, we know that because the write lock was held. This isn't going to change out from underneath us. Moreover, try convert to write lock will now work because we are a write lock, right? We got here the second time because we're a write lock. So in that case, we'll go through this code, and we will have succeeded. But the key thing to remember is that we had to release the lock and try to reacquire it, which provides a window for things to change, and this write lock may block. So we had to loop back around again and recheck the state. Now this is very important for your assignment 4B, because in assignment 4B, if you can't upgrade the read lock, you have to go back to the beginning and start searching at the beginning of the Palantiri map. And that was one of the very common mistakes we'll see when we look at the code in a minute that people got wrong. Okay, any questions about this? So the key thing to remember here is that we held the read lock so we could check this shared state to make sure it was the value we wanted. We didn't need a write lock at that point because we're just reading. And only if it's in the state we want do we bother trying to get a write lock. If it's not in the state we want, we don't want a write lock. Keep that in mind when you do the programming assignment as well. There are situations where you just scoot by the stuff that's in use and you only bother doing something when it's not in use. Okay, here is just the bottom of all this thing. You can see that when we're all done, we unlock the appropriate lock, which is either a read lock or a write lock, depending on the flow of the logic. So we use the version of unlock that doesn't know, doesn't care which type of lock you have. It'll properly unlock both types of locks. All right, so that's the most complicated of the examples, and that's the one that's most relevant to you. We're now at the end of our stamped lock discussion, and what we're going to do in this part of the lesson is I'm going to go ahead and talk about some of the usage considerations when you apply stamped lock. So the first thing to remember is under some scenarios, stamped lock may be way, way, way faster than reentrant read-write lock. There's a nice entry, a blog entry on the web that does a bunch of comparisons of stamped lock versus reader-writer lock versus just plain old synchronized blocks, synchronized statements. And the person who did the test found some interesting results. So what the person did is he compared the performance of synchronized statements with optimistic reads using stamped lock with reentrant read-write lock, and then with stamped lock that was not using the optimistic version. And he found the following results. Now, this particular scenario had 19 readers and 1 writer. So that's an example where you're not going to be changing things a whole lot. You're mostly doing reads. And so what he found in that particular case, as you can see here, is just one example. The optimistic reads were really fast because they weren't locking at all most of the time, faster than synchronized statements, way, way faster by several orders of magnitude than reentrant read-write locks, and faster than stamped locks that are using the more featureful stuff, not using the reentrant, not using the optimistic locks. So you can see that synchronized is actually pretty fast, but not locking at all is even faster. So take a look at that article. It goes into some more detail. However, as they always say for car commercials, your mileage may vary, right? So depending on what you're doing, you may get different results. So here is another example where the guy ran the tests again, except this time he had 10 readers and 10 writers, so there was a lot more contention for writing. And in this situation, he found that the synchronized block and the stamped locks performed about the same. They were pretty fast. Optimistic was about twice as slow, and the reason why that's happening, of course, is because when you have a lot more contention, whenever you do the try optimistic read followed by the validate, a lot of times it's not going to be valid anymore because someone's come along and written to the data structure, so you have to back off and revert to something else. So using optimistic reads really only works, to go back to Adam's question, if you have a lot of reads relative to writes. If you have a lot of writes, then you've got all this contention. And you can see here that, again, a reentrant read-write lock just kind of sucks across the board. There's almost no scenario where a reentrant read-write lock is any good at all. So it's pretty hopeless and pointless as an abstraction. OK, so the thing, stepping back, reader-writer lock speedups, such as StampedLock, are really only useful under certain conditions. So if you have lots of reads versus writes, ideally you'll have a lot more reads than writes, then a reader's writer lock is a win. If the read operations are non-trivial, then that may be helpful. Otherwise, locking costs will dominate. If there's contention for data, so if you have lots of contention, you'll have issues with reader's writer locks. If you have low contention, then low write contention, then that's good if you have lots of concurrent readers. And you also typically need a lot of cores. If you have a single core machine, then by and large, reader-writer locks don't really give you much of a win unless you're doing I/O-bound kinds of jobs. And even there, you have to be very careful. So these kinds of mechanisms really pay off if you have lots of cores, because then you really do have the potential for a lot of concurrency. StampedLock is more complicated to use than reentrant read-write lock. There's a lot more methods. You can see here many more methods. More intricate semantics and usage patterns, like the stuff we were talking about a few minutes ago with respect to lock upgrading and conditional writes and so on. You can take a look at this link for a nice tutorial where the speaker Hines goes into a great deal more detail about all these different approaches. And then there's also the following. It's very tricky to use StampedLocks if there's subtle invariance when you have optimistic read locks. And that has to do with the fact that there's really no coordination between how the various values are seen by a thread that does an optimistic read. So let's take a look at an example here to make this more clear. So in this case, we're going to have a class, and it's got x and y values. And you can see that it starts out where x is 0 and y is 1. And then down here, you can see we have a thread 1, which is going to grab the write lock, increment x, increment y, release the write, or grab a write lock, increment x, increment y, release that. Now, if this was a kind of a classical, fully synchronized based approach, the invariant that x is always 1 less than y should be preserved when you go to a thread that's going to be accessing these values. But down here, notice we're using an optimistic read as opposed to a read or a write lock. And so as a result, there's really no deep guarantees on the order in which this thread is going to see x and y. And so as a result, it may turn out that x has the value of 1 and y has the value of 1. So you may end up with x minus, or 1 minus 1 equals 0, and now you're dividing by 0 and all this kind of stuff. So the point here is that you need to be very careful if you have these complex invariants that span across fields that you're trying to access with an optimistic read lock. And if you go here, you can find out more about why this is tricky and awkward and so on. So I recommend you take a look at that. So the point is, you have to be careful about what assumptions you make when you use optimistic reads, because of the fact you're not really synchronizing it. You're just simply kind of getting a new value read into your cache. But that may be tricky if different threads are doing things in different ways. And also, the reentrant locks are not reentrant, so you have to be careful not to call them recursively and so on. Despite the complexity, StampedLock is the best choice for readers-writer locks in Java 8 if you're using reader-writer locks. There are other mechanisms that Java 8 provides, like atomic references, and Java 9 provides these things called var handles that may give you other features and capabilities for other things. But if you're doing reader-writer operations, then StampedLock is really what you want to go with. OK, so that's the end of that